Good afternoon, everyone. My name is Professor Andrzej Wilendowski. I'm head of School of Mathematics and Physics, which hosts this Lincoln Math and Physics Week 2021. Very warm welcome to everyone who came. In few minutes, we start. We're just waiting for maybe a few more people to come. During our session, you can ask questions in two ways. Either putting them directly in the live chat of YouTube, or if you would like to do it fully anonymously, there is a link at the top of the chart you can find to so-called Padlet, where you also can type in your questions, and then they are fully anonymous. In the beginning of our afternoon will be my short presentation about hosting school and university of these lectures. And those who come to every our lecture, you hear the same introduction, but some people come just for one lecture. After that, this is very short, just a few minutes, and after that we will listen talk about algebra from Professor Evgeny Khukhro, and we'll be able to ask him various questions afterwards. Welcome to our afternoon. Hello everyone, I'm Professor Andrzej Wilendowski, Head of School of Mathematics and Physics at the University of Lincoln, which hosts Lincoln Math and Physics Week 2021. This week forms a part of British Science Week, which runs also the same dates. This year we have our events, lectures all online. Traditionally, in previous years, you would come to our public lectures to our lovely campus by the Brayford Pool, by waterfront. This is how campus looks in the evening. But today we do it online, and in my introduction, I just would like to give you a few words about our university and the school which organizes these lectures. Lincoln is a small city for approximately 100,000 inhabitants. Our university is right next to the center, just about 10 minutes walk. City itself is quite old. It was already found by Romans soon after they came to the British Isles. Once it was also base of famous Legion 9 Hispania before legionnaires moved to York. The city received quite early in 86 prestigious status of a colonia, so it became Lindum Colonia, and Lincoln name came later on, and that already happened in times of Emperor Domitian. The place had a forum and a bath and all facilities of Roman times, and was a place for retired legionnaires. Even today, you still can find remains, Roman remains, and you can walk or drive under this Roman arch of Roman gates. The only one in Britain through which traffic is still allowed. Next big step in Lincoln development was in times of another visitors. Then William the Conqueror, William I, came to British Isles. Very soon he ordered to build a famous Lincoln Castle on the top of Lincoln Hill. And some years later, also even more famous Lincoln Cathedral started to be built just opposite to Lincoln Castle. This cathedral is considered to be one of the most beautiful buildings, if not the most beautiful cathedral in Britain and probably around the world. For some period of time, that was in fact the tallest building on the planet when a wooden spire was on the top of a main tower. Cathedral is, of course, was a seat of learning already from Middle Ages. However, university appeared in Lincoln much later, in the end of 20th century. Campus by the waterfront was opened by Her Majesty the Queen. And much later, already in 21st century, College of Science was opened, which included School of Mathematics and Physics, which opened its doors in 2014. And 3 years later, we also opened our own building, which we share with schools of engineering and School of Computer Science. And just in about months, we will be celebrating 4 years of this beautiful Isaac Newton building, named after Isaac Newton, a gentleman who also comes from Lincolnshire. And our lectures are primarily aimed at those who study mathematics or physics at A levels. Of course, they're accessible to everyone who is curious about maths and physics. But maybe those who study a maths and physics level will think about continuing their education after the school. And therefore, I'll mention what our school has here on offer regarding degrees in maths and physics. As you see, we have full range of degrees, bachelor, 3 years degree, and integrated masters, both in mathematics and in physics. We have also various combinations. For instance, combination of another Asian subject, one of most Asian subjects, philosophy. So we have degree in mathematics with philosophy and physics with philosophy, where philosophy is a minor component and physics or maths are major component. And we have also combination of mathematics and computer science and mixture of mathematics and physics as well. And with that, I welcome you to our next event in Lincoln Maths and Physics Week 2021. And I hope you will enjoy it. Welcome. And now we move to our main program, which is a lecture by Professor Evgeny Khukhro on algebra. Before start of the lecture, hello, Evgeny.
Hello.
Good to see you. Just a few words about our speaker. Evgeny Khukhro received his research degree, PhD, doctorate degree in 1980 in algebra, specialty from Novosibirsk University, which is in Siberia. Later on, 8 years later, he obtained his highest degree in Russia, so-called Doctor of Science in a group theory from famous Sobolev Institute of Mathematics as branch of Russian Academy of Sciences in Siberia as well. He continued work as a researcher in Novosibirsk as well. In beginning of 90s, he spent several years as Alexander von Humboldt Personal Fellow in Albert Ludwigs University in Freiburg in Germany. since middle of 90s, he moved to United Kingdom, where he worked on various research and teaching positions in University of Cardiff and University of Manchester. In September 2014, Evgeny joined the School of Mathematics and Physics here in Lincoln as a founding program leader of mathematics. He is a director of a research center for algebra named after Charlotte Scott. He is author of research monographs, books, editor of 3 journals, and we are very happy that he can talk today about algebra. Floor to you, Evgeny.
The lecture is called Group Theory, Algebra of Transformations. Well, in every part of mathematics, most important things are transformations, which preserve certain structures. These can be called generalized symmetries. Here are a couple of examples. When we study geometry on the plane, the structure means distance. When we study shapes of figures, and therefore transformations which preserve this structure are transformations which preserve the distance. And such transformations are exactly the following. There are mirror reflections in some axes, there are rotations about a point, there are parallel translations of the plane, as well as various combinations of these transformations. Quite a different example is about polynomials or equations. Consider this equation in 3 unknowns. So, as transformations, we consider changes of variables. Preserving this equation means when you have change of variables which does not change the equation, does not change this polynomial on the left. So, for example, if you change variables like this, x1 substituted by x2, x2 by x3, x3 by x1, you see the structure of this equation is such that this change of variables does not change, does not alter the polynomial. But some other changes will be changing the polynomial, so these are not transformations which are allowed for this equation. Well, in various parts of everyday life we also have transformations, like in this famous Rubik's Cube we have transformations which are allowed, and these are also transformations preserving the Rubik's Cube. And when we consider all transformations of a given object, usually a mathematical object of course, all transformations form a group. Here the word group has certain precise mathematical meaning. It's not just any group in common language, but there is a precise definition which we shall consider. Again, here is an example from elementary geometry. Consider a square ABCD on the plane, and consider the transformation of this square as a rigid figure. So such transformations are also called isometries when all distances are preserved. And it's easy to understand that actually we have only 8 such transformations. There are 4 rotations about the center O, so we include rotation through 0 degrees, which is of course does not really change anything, but just for completeness we shall see that this is important to have such transformation which does not change anything. There is of course rotation through 90 degrees, through 180 degrees and 270 degrees. For definiteness, let's consider counterclockwise rotations through these angles. And there are of course 4 reflections. There is a vertical axis, horizontal axis and 2 diagonal axes. Altogether we have 8 elements, and these 8 elements form the group of isometries of this square. There is a special title for this group, D8. Well, importantly, in every group of transformations you can do multiplication, sometimes also called group operation or group composition. So this is not ordinary multiplication of numbers, but is defined simply as consecutive application of such transformations. So if you have 2 transformations, G and H, preserving some object A, we can simply perform one after another. So every element in A is sent first by transformation G, so you form the image G of A, and then you apply H afterwards. So as a result you have this image H of G of A. This can be drawn on a picture. The same object is simply depicted 3 times for clarity. So our first transformation sends an element by this arrow, then we apply another transformation, and the resulting transformation, which is here denoted by G circle H, is simply the composition of 2 transformations G and H. And in group theory we simply say that this is the product denoted by G circle H when you apply G first and then H. Well, in fact, in some books this is written the other way around, but we stick to this definition as on this slide. Well, importantly, a group is closed under such multiplication. And this is quite clear because if both G and H preserved this structure A, then you preserve once, you preserve twice, the composite G circle H also preserve the structure. And what it means that if you have this group of all transformations preserving the structure A, then this group is closed under this multiplication of transformations, under this product. When G is in G and H is in G, then the product is also in G. And this can be seen also in that example with the square. So let's introduce this notation: A, B, anti-clockwise rotation through 90 degrees about the center, and let B be the reflection in the vertical axis. So what is the composite? What is the product A circle B? Well, this can be determined simply by looking at where some vertices go. Let's have a look where A and B go under this product AB. So A, under rotation, A goes to vertex D when you rotate, and then you reflect in the vertical axis, so D goes to A. So the resulting composite product AB sends vertex A to A again. And if you look at where the vertex B goes, under rotation B goes to vertex A, then reflected to vertex D, so the product sends B to D. So what we see, A is fixed and B goes to D, and of course we know that the composite must be one of those transformations. And the only possibility is obviously the reflection in the diagonal AC, because A is fixed and B goes to D. The only such transformation is reflection in AC. Well, it's possible to compute other products of these other composites of A and B. For example, if you do A squared, we use the usual notation for powers, but of course this is not ordinary multiplication of numbers, this is composite of transformations. If you rotate through 90 degrees, then again rotate through 90 degrees, the result is rotation through 180 degrees. B squared is identity transformation, which doesn't move anything, because if you do a reflection, then again the same reflection, you simply send every point back to itself. Also, if you do rotation through 90 degrees 4 times, you return every point to its original position, so A to the 4 is also E, also the identity transformation. Well, we can compute another product like this. What if we compute B circle A? We computed A circle B, but now compute B circle A. A goes to D first under B, then to C, so reflected and then rotated, so A goes to C. B goes to C under reflection in the vertical axis, then rotated goes back to B. So B goes to itself and A goes to C, so this composite, this product B circle A must be the reflection in the diagonal BD. And this is interesting because this is not the same as A circle B. A circle B was reflection in AC, but B circle A is different, reflection in BD. If you also compute A cubed B, A cubed 3 rotations, then reflection, A goes to C, and B 3 rotations goes to C, B to B, so this is again reflection in BD, because B goes to B and A to C. And here we see that this is the same as the product B circle A. So we have this equation now. B circle A equal A cubed B. Another nice property for transformations for this product is associativity. It means that you can put these brackets either this way or this way. A circle B circle C is the same as A circle the product B and C. And this can be seen on this diagram. If you do like this, it's the same as if you do like this, applying A and then the product BC, or applying product AB and then C. Is really the same result, applying A, B and C consecutively. And this is a good thing to have associativity, because then we can write without brackets simply as the product A times B times C. Here is an important moment. So we have this group D8. Usually we do not really write circles in groups. We just know that this is not ordinary multiplication AB, the group operation, the composite. And our group of symmetries of the square consists of these 8 elements. We have these rotations, including the identity transformation, A squared, A cubed, rotations through 90, 180, and 270 degrees, and the reflections. These are all the elements of D8. And we also have these relations. B squared is E, A to the 4 is E, and BA is equal A cubed B. And this is the important moment. We say that we consider the abstract group when we simply forget that square from which it came and simply work with these elements using these relations. This is now an abstract group consisting of these elements subject to these relations. And then we have a kind of calculations in a group. We can solve equations, for example. Let A and B be the same elements as on the previous slide. And we want to find x such that AB times x times B is equal to BA for those elements A and B in DA. How do we solve the equation? Well, we can simply multiply by inverses. Because we have our relations. We say that A inverse is A cubed, because A to the 4 is identity element. Inverses in groups are elements such that they produce identity element when multiplied by, because A times A cubed will give you identity element because of this relation. B is its own inverse because B times B gives identity element. So the idea is to use inverses, multiply by inverses, but importantly we have to be careful and choose on which side to multiply by inverses, because groups are not always commutative. You have to be careful. If you multiply by the inverse, you have to multiply on the same side. So here we want to kind of free or extract this x on the left, express in something on the right. So what we do, we multiply by A inverse on the left both sides, then by B inverse, and also multiply by B inverse on the right. This is how we solve this equation. We multiply by A inverse first on the left, then by B inverse on the left, and by B inverse on the right. Then on the left, those inverses will simply cancel out, and what we'll have exactly the expression for x. It remains to simplify this product, this composite of group elements using the same relations. We simply write that B inverse is B itself, A inverse is A cubed, then BA, B inverse is B again, and then we can use those relations. We can rearrange BA here, the product BA is A cubed B by our relation. And then we can consider other such occurrences. A cubed times A cubed is A squared, because A to the 4 is identity element, and so as a result we simplify to A squared B. This is how we solve this equation by multiplying by inverses. This is a calculation in an abstract group. We no longer need the square, we don't need to look what are the rotations or reflections. Well, this is the definition of an abstract group. A group in mathematics is any set of elements with an operation which is called multiplication, but it's not ordinary multiplication of numbers. First, it must be closed under this operation. Operation must be associative, and there must be neutral element, identity element E, such that EA equal AE equal A for all A in G. And also every element must have an inverse, denoted G inverse, such that G times G inverse is equal to identity element E. So the standard example of groups in mathematics is the group of transformations preserving a certain structure. Simply consists of all one-to-one mappings of the underlying set, and the operation is the composition when you perform transformations one after another. All these axioms, all these rules are satisfied automatically for transformations. We saw the associativity, we know there is inverse transformation, and there is of course the identity transformation which makes these rules hold. Well, group theory studies groups in their own right. And group theory is a strong point of algebraic research in our Lincoln School of Mathematics and Physics. This school is new, it's a new department founded in 2014. To have some idea of what kind of research is conducted in group theory, in particular in our School of Mathematics, let me give a bit more definitions. And here is the definition of commutative groups. We saw that groups are not necessarily commutative, but if all elements commute, AB equals BA for any elements in the group is said commutative. And this is quite a nice property, of course, so getting more commutativity is a good thing. Here is an example of such a theorem. Suppose that you have a group in which G squared is identity element for every element G. Then you can prove that G is commutative. To prove, we simply consider any two elements AB and use the fact that the square of the product is identity element. AB times AB is E. Multiply this by A on the left, both sides, and by B on the right, we get this equation. Now we can rearrange brackets because of associativity. We get AA times BA times BB. But AA is also square of an element, and they are all squares are identity elements. So we get EBAE equals BAB. Identity element can be dropped, so BA equals AB. As required, this is for any two elements. It means the group is indeed commutative. And in fact, many parts of my own research are about obtaining kind of greater degree of commutativity of the group. To give you some idea of what kind of degree of commutativity we are talking about, I need to introduce another definition, a measure of non-commutativity. Such a measure is the so-called commutator of two elements. The commutator is denoted by square brackets and is simply the product of A inverse, B inverse, AB. So you see, if A and B commute, then you can rearrange these elements and obtain identity. So this commutator is identity exactly when A and B commute. If they commute, you can rearrange, you get identity. If this is identity, then again you can multiply by BA on the left and get that AB equals BA. So indeed, commutator measures non-commutativity, and the group is commutative exactly when all commutators are equal to identity element. And some non-commutative groups can be defined which are close to being commutative to some degree, and these definitions are in terms of commutators. One such definition is of soluble groups. When you take iterated commutators of commutators. For example, if you iterate commutators like this is the definition of soluble groups of derived length 2. You can iterate this construction again and again, which gives definition of soluble groups of derived length k for any positive integer k. By the way, soluble groups appeared first in Galois theory. Group theory as a whole actually appeared in Galois theory, which gave answers to the question of solubility of equations by radicals. To be precise, with every equation you can arrange a group of permutations of its roots. This is known as the Galois group of this equation. And then the equation is soluble by radicals exactly when this group is soluble, as in the previous slide. And actually the very term soluble group comes from this solubility by radicals. And by the way, there are equations with non-soluble Galois group. For example, this particular equation is known to have non-soluble Galois group, and therefore there is no formula to express roots of this equation by radicals. Unlike quadratic equations or even cubic or equations of degree 4, they do have formulas for roots in radicals. But starting from 5, this is not always possible. Anyway, there is another way to define groups which are non-commutative but closer to being commutative when you iterate taking commutators in a different way. These are called Nilpotent groups of class C. If you take such commutators, if they are equal to identity element for all elements in the group, then the group is Nilpotent of class C. And with these definitions I can now show you some recent paper of the result of research conducted in our school with collaboration with other researchers, in this case with Brazilian mathematicians. So if you look more closely at the abstract of this research paper, you will see groups are defined using those commutators, iterated commutators, and these words nilpotent appear here. So this should really give you some glimpse of research results in group theory. Research conducted in our School of Mathematics and Physics. Well, in general, group theory in mathematics studies groups in their own right, as I mentioned, and this is really a very diverse and rich theory. New results and methods appear all the time. Many papers are published. There are many open problems. Various methods of study appear. And also group theory arises in many parts of mathematics. I already mentioned Galois theory. There are also other parts like algebraic topology, algebraic geometry. Even in differential equations, groups are used for reduction of dimension, in cryptography, and in many other parts of mathematics. Well, even in natural sciences, groups are used as measures of symmetry in crystallography, quantum physics, in material science. And here is just a few titles of books where group theory is applied in various parts of other sciences, in chemistry, physics. Well, concluding this lecture, I would like to say that many algebraic structures like groups arise as abstractions from various mathematical objects and theories. But then there is payback benefits. Algebra, group theory make these theories and objects more transparent, provide answers, techniques, and insights. As a famous mathematician D'Alembert said, algebra is generous. She often gives more than is asked for.
Thank you very much, Evgeny, for your wonderful talk. Now there is time for questions, and questions can arrive either in YouTube chat, just below, and also in the chat there is a link to Padlet, and I see during lecture questions arrived, and actually they continue to arrive, and I start to read them to Evgeny to answer. So there is a question here. What made you interested in this field?
Well, we had a very nice teacher at the school where I was studying, and it was actually a specialized school for physics and mathematics, and some of our teachers were actually university lecturers, and so they attracted us to their own fields of research, and especially in group theory it was possible to try to solve exercises even at the very beginning. When you start studying, you already have interesting exercises, and once you start doing this, you see that it goes well, then you kind of go into it, and if you're successful, then you like it more and more. And yes, it's a beautiful theory.
And then there is another question. Can algebra be explained only with Greek geometry?
No, I don't think so. Actually, Greek geometry used to be a basis for proofs in algebra, maybe in analysis more so. For example, in Newton's time it was the case, but later it was actually the other way around. It was the revolution by Descartes, who invented Cartesian coordinates, what we know now, and then it was algebra that solved all geometric problems, and nowadays it's usually algebra which is a basis for solving geometric problems as well.
Thank you. Then there is a question. What real-life applications does this have?
Well, as with mathematics, mathematics is usually the language in which natural sciences are studied, and mathematics can be developed in itself, pure mathematics. At the same time, it has applications, and applications drive the development of mathematics. And the same applies to algebra and to group theory. Groups are studied in their own right, as I said in the lecture, but also they are used as a language to describe symmetries in natural sciences, in crystallography, or in atomic physics, physics of particles, and so on. in other parts of mathematics, group theory is everywhere because it plays the role of providing classification of various parts in various parts of mathematics, and therefore it's really permeating all parts of mathematics, and in this sense it's everywhere.
Thank you. And then there is another question just arrived. Could this help us to understand asymmetries?
I suppose, for example, when people study the DNA sequences which determine our biology, you can use group theory as a language to describe substitutions of those elementary bits of DNA sequences. And in this sense, again, group theory can provide a language for studying these symmetries.
And then just also arrived question, where is there an example of a group theory in my everyday life?
Okay, well, in your everyday life, you can maybe doing your Rubik's Cube, and every time you're doing Rubik's Cube, you're actually exercising in doing transformations which preserve Rubik's Cube. And in this sense, it's group theory. But of course, otherwise, as with other parts of pure mathematics, you do not really see pure mathematics in your everyday life. You're not using it to cook your breakfast, and the connection is more involved. Mathematics is used for natural sciences. Natural sciences are used for producing certain technologies, and then technologies can be important. One good example is maybe using communication devices. All mobile phones and so on, they all use cryptography, and cryptography is based on properties of prime numbers, and in this sense, very pure science. Number theory used to be a very pure science, just like group theory. And it was developed for centuries as pure science, but now it's very much applied in everyday life. Actually, right now, when we using internet, it's all encrypted, it's all coded, and so on. And this is where you see everyday applications.
And just as you mentioned, Rubik Cube, there was also a question in the Padlet. You showed Rubik Cube. Can groups exist in more than 3 dimensions?
Oh yes, absolutely, yes. In general, algebra provides means of working in any higher dimensions, and of course there are groups of transformations of high-dimensional spaces. Even when you study linear algebra in your first year at university, for example, in Lincoln, you will be studying n-dimensional spaces and groups of transformations of n-dimensional spaces. And this is all very important in all parts of mathematics and in natural sciences.
And then there is quite a long question. Can the group theory be abstracted to the point we don't have to rely on Euclidean plane to examine the limits of mathematics?
Well, I already mentioned that group theory is already an abstraction, and it already is working without geometry. When we define this abstract group D8, we did exactly that. We made an abstraction of these transformations. We no longer look at the Euclidean plane. We no longer look at that square. We're working just with group transformations. So in this sense, the answer is yes.
And then I see there are a couple of questions related to Fermat theorem. How difficult is the proof of the last Fermat theorem?
Well, it is very difficult, and of course, you know, it remained unproved for centuries, and therefore it's quite natural that the proof is very difficult. And I think there are probably not very many people in the world who actually read the proof, maybe a handful of such people. And in this sense, there is still room for improvement. If you are interested in this, you can go into mathematics, you can try to find a shorter proof or simpler proof of Fermat's light theorem. And this would be very interesting and very valuable. And this, actually, there are many other problems which are still open, like the existence of Fermat primes. Fermat primes are the primes of the form power of 2 plus 1, like 5 is such a prime, and it is still an open problem whether there are infinitely many such primes or finitely many such primes. This problem is still open, and in general, in fact, there is some misconception that mathematics is something already done and dusted, but the better comparison of mathematical knowledge and actually any other knowledge is that it's like an island of known. There is an ocean of unknown, and we only know a small island in this ocean. And the bigger the island of known, the longer the shoreline, as you understand. So the more open problems arise all the time, and so mathematics is full of open problems.
And I see there is now a question in a live chat from Shani Nas, who asks, what advice would you give to a parent who wants to encourage their children, teenagers, to put algebra into practice?
Well, first of all, it's better to learn algebra in the first place, and then algebra in practice usually means algebra is applied in other parts of mathematics. And of course, it's also applied in applied mathematics, which has relevance to practice, like solving differential equations, which govern, you know, movement of planets, or if you want to send a rover to Mars, you have to calculate the trajectories and so on. And in this sense, applications of algebra are only via other parts of mathematics. And in this sense, the best thing to advise is to study algebra in the first place, and then see how it's applied in other parts of mathematics and in applications.
Thank you. And then maybe related would be question on Padlet, in which year this can be studied in university?
Oh, yes. Actually, in our mathematics program, we have a special module called group theory. And this is a module of the third year. But some other parts of algebra are studied also in year 1. There is algebra module, and there is a module of linear algebra. And then there is second year module, algebraic structures, and then module group theory is in year 3.
And thank you. I see we approaching end of our program, but let me pick up. There are quite a few questions actually in Padlet, and there is one which is, what is now the last Fermat theorem?
Well, I think the question asks what is the biggest open problem, but of course there are many open problems in various parts of mathematics, and it's difficult to pinpoint such a famous problem, because Fermat's problem had the advantage it could be easily stated, but in most other parts you have to give definitions, you have to go into these parts of mathematics, and it's not easy to state. But of course there are such problems, very challenging problems, which I really cannot state right now.
Right, and maybe a last 30 seconds question was also on Padlet. What is the most beautiful for you in math?
Well, mathematics is beautiful because it's rigorous. You prove a theorem, and the proof is, this is absolute proof. You derive properties, and there is no question. It's always correct if it's correct, and if it's incomplete, then it's incorrect. And it's very much like solving puzzles or riddles. And in this sense, mathematicians enjoy themselves. They are like children playing with beautiful things and solving riddles, puzzles, and enigmas.
Thank you very much, Evgeny. And with that, we approach to the end of our hour today. I would like to thank Evgeny again for his lecture and all the questions. I'd like to thank our public for listening, for asking questions. And I would like to invite you to join us for more talks. And in fact, the next talk will be just in a few minutes on the same channel. Thank you very much for coming, listening, and being with us. And thank you, Evgeny, again. And bye-bye.